Hello and welcome back to another lecture in CIT 130, Introduction to Java Programming. If you remember from the last lecture, we started to talk more in depth about object-oriented programming. I've mentioned several times during the term that by design, Java is object-oriented. And we can see that in the fact that everything in Java is defined as a class. If you remember from last time, we essentially said that a class is the definition or template for all of a set of particular objects. We define those objects with a thing we call properties, which are the descriptors. They're variables that are used to describe each object. And then we also have methods which act on or with those properties in order for us to use the object the way it was intended to be used. For this, we decided to make a very simple class for a rectangle. Thinking about a rectangle as something that might appear not only in everyday life, but may also appear inside of individual programs. And it's something that can be defined very simply and very easily with only two properties, its width and its height. And then we had a very simple set of methods that allowed us to interact with those properties to change them and to look at them, and also to calculate some other descriptors that depend upon the properties. Those are the things we did in the last lecture. One thing I want to reiterate is that we create our properties as private. That allows us to protect the data integrity of those. Defining width and height as doubles means that they can carry values that are both positive and negative. But in general mathematics, a width or a height that is negative doesn't make any sense for a geometric shape. By making them private, we cannot access them directly from outside of the object. We have to use something public in order to get at them. And so we typically will make what we call set methods that are public that allow someone to attempt to assign a value to those properties, but we can protect the integrity of that data with some kind of data protection through an if statement, like this, where we prevent anyone from changing the value to something negative. It simply does not make the change. Since our properties are private, we can't read them if we can't set the value of them. We can't change them. So we also generally have these get methods which allow us to access those properties for viewing what their values are or in order to display them. All of our methods are public because, again, public methods mean we can access them from the main program. And as an example of that, just as review, let's look at our rectangle test that we created, where we create objects from the class using the default constructor. That default constructor creates rectangles that have 0 for both the height and the width, because by default any properties within an object that are numeric, if we don't set them at the time the constructor is called, they're just set to a value of 0. And then in order to take a look or work with those rectangles, we were able to call methods on them, because the methods like set width are public. So if the properties were public, we could do r1.height equals -3. But because we want to protect the integrity and not allow negative numbers through the dot operator, we make our methods public and our properties private. That is the rule of thumb that you will follow throughout your career in developing Java. As with anything, there are exceptions, but especially now, don't think about that. Just think about the fact that we want to access those variables inside the objects through the public methods. So today we're going to continue with our object-oriented programming and design by expanding a little bit on this rectangle class. When we think about objects of any given class, we want to think about them sometimes in a much bigger picture. As I said, we use the properties, the variables within each object to describe the specifics of that object. From a geometric mathematical standpoint, we can describe any rectangle based on its width and its height. And we talked about the value of those sets and gets since we made the properties private. And then we allowed to do some more complex calculations, which again helps us to describe and think about the rectangle in a broader sense. But there's some more general purpose things that we often do with objects, and so we build them into our classes. The first we're going to do is we're going to go a step deeper into this idea of a constructor. By default, every class you make has a no argument constructor, a constructor that takes no input, that simply does nothing and allows any of the members, any of the properties within that object, just be set to 0 if they're numeric, false if they're Boolean, and null if they're objects within objects. But a lot of times we want to do something different. We want to have control over what happens when somebody calls a no argument constructor. So let's build our own constructor that has no arguments. Now, one of the things we're going to see immediately is that we do not have an output type when working with constructors. They will be the only methods we create where in between the access modifier and the name of the method, we don't see an output type, not even void. That's one of the characteristics of a constructor, because technically the constructor is not called in a traditional way. We're not taking an object, calling a method on it, and then having something returned or nothing returned. What we're actually doing is we're creating the object, and so we code it by putting it inside the class, but it doesn't really have an output type. It just spawns or creates an object through the new keyword, and then it's the new instance of that class. That new object is assigned to the reference variable on which we call that new and the constructor. The second thing is the constructor must always be named identical to the class. So it will be a method where we start it with a capital letter because we start all classes with capital letters. So we really don't have any leeway here. Once we declare the method as public so that it can be accessed outside of the object, it's just going to be named the same thing as the class, and it's going to have no return type. We'll talk about inputs to constructors very, very shortly. But let's just finish out our no argument constructor by basically saying the generic or base rectangle object has a width and height of 1. And I should put the point 0. They are floating point variables. And now we don't have a rectangle of 0, 0 when we call these no argument constructors over here. They'll change to 1 by 1. We can see that by going out and recompiling and rerunning everything. Remember, I just made a change to the rectangle object, so I do have to recompile that. So I do java c rectangle.java. And then I can recompile just to make sure there were no changes to the test program. And then we can invoke the Java virtual machine with the runnable class file. And you see that each of the rectangles now is 1 by 1. If you review the last lecture, you'll see when we called the no argument constructor that was given to us by default, they were both 0 by 0. So now I could do something like a 3.2 by 8, and then that makes it that makes that version of the rectangle, and you'll see that the second rectangle is still 1 by 1. Now, one of the things that we may be thinking is, well, sure, it's great to have this constructor that has no arguments in it, but sometimes someone may want to define the height and width of the rectangle at the point when they're making it. And that is something we can do. So I can make a second constructor, rectangle, and we'll take in a double W and a double H for the width and height. And we can do, similar to what we did down in the set methods, we can basically say if W is greater than or equal to 0, we can do width equals W, and we could say else width equals 1. That way we have we still have a value from the constructor. We could leave it off, and in that case it would make it 0 by 0, but to keep the spirit of the original constructor, we'll do it this way. So we'll do the same for height. If h is greater than or equal to 0, we will make the height equal to h, and otherwise, we'll make that height equal to 1. Now, there's a couple things that we have to kind of address here. The first thing that you may be thinking to yourself is, how do we have two different methods that have the same name? That's going to cause us some kind of problem. Well, the reason it doesn't is, if you remember when we first talked about methods, even before we were going into object-oriented programming, we talked about each method having a signature. So the signature for this first method is name equals rectangle, number of inputs or arguments is 0, and types of arguments is, not applicable or none or whatever you want to call it. Because our signature is defined by the user-defined name for the method, how many inputs or arguments go to it, and what the types of those arguments are. So looking at the second one, the name is again rectangle. The number of inputs equals 2, and the types of arguments equals double and double. So what we've done is we've created two methods that have the same name, but they have different signatures. That means they can be identified when calling them. I mentioned briefly in the lecture on methods that the output, which of course here there is none, is not part of the signature. That's because when we call a method, we call it by name and send it values or variables that match the data types for it, the signature. That means as long as in a program like this rectangle test that uses the methods, as long as it is immediately obvious which version of the method to call from here, two methods can have the same name. There's a fancy term for that. When two methods have the same name in the same class, but different signatures, we are said to be overloading that method. One of the very, very common places to do overloading is in constructors. Now, there are two different ways to do constructors like what we see here, like this one here with the that creates one given a height and a width. Because if you remember from last time, we did this set method here, and you'll notice that to some degree I've repeated my code. In this case, because it's not an exact duplicate, I would leave it. But let's say instead of having the default be 1, I wanted the default to be 0. What I might do, oops, I wouldn't need the else there anymore. What I might want to do to prevent maintaining two sets of identical code is actually call the setWidth function and pass it w, and then call the setHeight method and send it the height to do that work. This is a perfectly acceptable way of doing things because the methods are part of the same class definition and part of any object made from that class. So we can do that. Again, in this case, I'm not going to, but I did want to at least explain that as an option so that you would be aware that that is something that's available to us. But because at construction time, I don't want to wind up with a 0 by 0. I want the person to explicitly say 0 by 0 if they want it that way. I'm going to have slightly different code here than in the sets. So for me, I'm going to go ahead and make and code it out in both places. And in that case, height will equal 1.0. So this is a common way to go about doing our constructors. And you'll find that having multiple constructors is very, very common within within the language. So if I say go to java.lang.float, you'll see that I have a few different constructors. We have one that takes in a double, one that takes in a float, and one that takes in a string. In this case, there is no argument constructor, but no argument constructors are extremely common. But overloading our constructors where all three of these have the same name, all three of these have one argument, but in one case it's a double, in one case it's a float, and in one case it's a string. Therefore, when calling the constructor, the virtual machine will have no difficulty determining which of the three methods to use because that signature is different. What I'm passing in to the float lets it know which one to use. So that gives us kind of the concept of constructors and how they work for us. There are a number of other things that we can do with our objects and therefore our classes. In the past, you've seen us compare two strings using the dot equals rather than the double equals sign. That is because when comparing two objects, comparing with a double equals is actually comparing if it's the same object rather than two different objects that are identical. Essentially, for now, the best way to think about why we use the dot equals versus the double equal sign to compare objects is if you, as my student, referred to me as Brian, but my child refers to me as Daddy, both names, both variables, both addresses to me are still me. In that case, Daddy and Brian are both me. That's where we use double equals. That means Daddy double equals Brian is true in that case. But if we took a set of identical twins where all of the properties of each of those people were the same, they are dot equals. But if one, say, his name was Ian and the other's name was John, we would say that Ian dot equals John is true, but Ian double equals John would be false because they're still two different people. They're the same, but they're not the same object. They're indistinguishable maybe, but they are not the same thing, the same object. So it is very typical to create a dot equals method for any given class, because technically we do get a dot equals without writing one, but that works the same way as the double equals. So in most cases, we're going to get false when we expect to get true. So what we'll do is we'll do a public Boolean equals method, and it will take in an object of the type of this class. So this is a little bit different. We're going to be receiving an object of type rectangle, and we'll just call it R. And we will compare the passed in rectangle to ourselves by checking the value of the width and the value of the height. If the width and the height are the same, the two rectangles will be indistinguishable from each other, but they'll still be two separate rectangles. So what we would do is we would say width, that's the member value, because remember each object, each instance of the rectangle has its own width, and we copy those properties and methods into each object at construction time. So we're checking my width against r dot get width. So what that does is I compare if they're the same. If they are the same, then we will return true. Otherwise, we can return false. Hopefully that makes sense. If the width of the passed in rectangle is double equals to the width of myself, then we always use double equals with numerical values because that's the way primitive types work. So the get width, which returns the double, the width of R as a double, is identical to mine, then we'll return true. The values are they're equal, but it's not just width, right? We need to make sure it's width and height. So now I check my height against the get height of R. And remember, with our logical and, remember that truth table we talked about in early on in the class, we're basically saying that the width of both items have to be the same and the height of both items have to be the same. So if one or the other is different, we won't return the true. It'll only be the same if both width and height are the same in the source rectangle, the one we call the method on, and the one we pass into it. And this sort of construct is the way that equals methods are generally written. We have the method inside of the rectangle object itself that we call, and we pass in the object we want to compare it to. That's how dot equals methods are expected to be written. That's the convention that sort of by default or de facto has been established within the community of those who create equals methods. It's also not uncommon to create a compare to method. Sometimes we don't want to just know if they're the same. Sometimes we may want to know if one object is, say, greater than or less than another. Generally, we do that in a way that sort of makes sense to us. And the way I want to think about it in this case is we'll say that one rectangle is bigger than another rectangle if the area of that rectangle is bigger. Typically, when we work with compare to methods, how we, by convention or by the de facto standard, how we think about it is if the calling object is smaller than the passed in object, comma, we return a negative number. If the calling object is bigger than the passed in object, we return a positive number. When the two objects are equivalent or equal, we return 0. This is the convention for compare to methods. And what we find, what makes sense to us about this, why this convention is chosen, and why we return a numeric that's the same as the type of the measurements that we're using, is we can use simple calculations to return what we're talking about. So what we can do is we can call the area method from myself, which is going to return my own area, and we can subtract r dot area. So my own area minus the area of the passed in rectangle, if my area is smaller, that's going to yield a negative number. If my area is bigger, it's going to return a positive number. And if the two areas are the same, that's going to be 0. So now all I have to do is just say return that calculation. And I don't have to create a variable to do so. I can just do the calculation and return that. What it'll do is return the answer of area minus r dot area. It's basically an anonymous value. We don't have to give it a variable, name the value, if all we're going to do is return it. So that's something you'll see a lot in programming. We did it in area down here. We did it in perimeter down here. This is very similar. And this meets that convention, just like I said. So by using this convention in all our compare to methods, we create a very simple way of calculating it. I don't care how much below zero the areas are different. Just if it comes out negative, I just know the second rectangle is considered to be bigger. Another thing that is common is to see a string representation of an object. I want to show you how that works by default, and we'll talk about, and that'll give us a chance to test this equals and compare to as well. And then so we can see why we want to make our own. So what I'm going to do first is here, before we make any changes, let's do system.out.printf. It is %b that the first and second rectangle are equal. And actually, since I haven't saved and compiled the rectangle, let's see, because by our own standards at this point, two 1x1 rectangles should be the same. So let's look at it. Let's just compile the rectangle test with the equals in there. So it's not going to have the code I wrote because I haven't saved and compiled the one I wrote. And let's see what happens there. Since we talked about it, I made a mistake. Strangely enough, I forgot to put the comma R1 dot equals R2. I forgot that. So this returns a Boolean, a true or a false. So I made a mistake, left that out. You probably saw it coming. Let's recompile. Let's rerun. And we're below the screen. Let's pull it up. And we see that it is false that the first and second triangle are equal, even though, again, by our standards, they're equal. That shows you why I needed to write this one in here. Now if I save that, and we'll exit out, we'll recompile both the rectangle and the rectangle test. Oops. To see, now it shows true that they're equal, because we're using our concept of equivalence. Now let's throw in the compare to, and we'll do that after we change the rectangle R1. Now what we can do is we can say system.out.printf. Actually, I'm going to do it in a set of if statements. If R1.compare to R2. See, we can pass, we can actually pass a rectangle object there. R2 is a rectangle. If that is less than 0, let's take this, and we'll say the first rectangle is smaller than the second rectangle. And likewise, if we do R1 dot compare to R2 is greater than 0, we can, oh, and we don't need a printf anymore because we're not going to actually print that number out. We'll do it as a print line. System.out.println, and we'll just say the first rectangle is larger than the second rectangle. And if they're not, it's not greater than or not less than, we know it'll be, it'll be equal to 0. So I can just put it as an else case. I could, in theory, set if it equals 0, but there's no necessity to do that. And else cases are safer, especially if there's going to be some kind of value set in here. We mentioned it briefly when we did decision statements, but just to reiterate, the compiler only sees these as each if statement as possibly being true or false, and if we never have one that's just plain else, it may think none of them might run. Now I can just say the two rectangles are equivalent. And now, if I do that, let's take a look. I think that I haven't changed the rectangle, but I went ahead and recompiled it anyway. Now, they're starting it as true that they're equal. And now, if I make the first rectangle 3 by 4, we would in theory think of the first rectangle as being larger than the second rectangle. The first rectangle is 3, has a height or a width of 3 and a height of 4 for an area of 12, a perimeter of 14. The second one is 1 by 1, and indeed the first rectangle is larger than the second rectangle. Just as a means of showing it, what I could do is I could say the second rectangle, and I'll put some parentheses inside there, and do a %s for a string. And that comes before those two. If I do R2 dot toString, let's see, that's something that's going to return a string, as you might imagine. It's going to be a string representation of that rectangle R2. Let's see if I don't write a toString, what does that look like? This is after the we put in the new values for the first one, so we'll just make it 3 and 5. And we see, this is what I wanted to see is right here, the second rectangle at 12 EDCD 21, has a width of 1 and a height of 1. Well, that may seem very strange to you. You're thinking, what does rectangle at 12 EDCD to 1 mean? By default, just like the default constructor gives us the 0 by 0 rectangle, by default, our toString method returns the class name. So what it means is something that is this, a rectangle, and it lives at 12 EDCD21. This 12 EDCD21 is a hexadecimal address where the object lives in the RAM. So that may not be very valuable to us as a representation of the object. That sometimes can be helpful if we're writing very complex code and we need to debug and we want to make sure what kind of object we have, and some things like that. But for a program that's going to be used by a user, it's going to be way better to have something more descriptive. So it's very common for us to create a public string toString method. Has no inputs because the object being turned into a string is the one we're calling the method against. So we don't need to have, send ourselves to us to do this. And what we typically will do is return some kind of representation. And what I'm going to do is return the width concatenated to a space and a capital X to represent sort of by, because we would say a rectangle is like 1 by 1 or 3 by 5. So we do the width by the height, and we concatenate it in the middle here, so that in the end we wind up with, say, 1 by 1 instead of rectangle at that hexadecimal address. So let's save that. And let's go ahead and recompile the rectangle. Now I didn't change it, but we'll recompile the test for good measure. And then we'll run the test. We'll make this that first rectangle there. Now we see the second rectangle, 1 by 1, has a width of 1 and a height of 1. Now we have a string representation of the object, which makes sense to us. So again, that's something that's very typical and very common to do. Now there's one additional method that is fairly common to do, and that is what we call a copy method. And our copy method is essentially going to return a rectangle. So it's not a constructor because it's a method called from a rectangle, but it's still going to produce the output of a rectangle. And we don't have to pass anything to it because it will be copying itself. So if we do r1.copy, that will create a new rectangle that we'll have to put into a rectangle object, or a reference variable. But essentially what we would typically do is we would call a constructor to make a new one, where we might say return new rectangle width, comma, height. So what that's going to do is create a new rectangle by calling this version of the constructor double WWH, and we'll pass our own width and height to it, and then that rectangle will get returned. Don't forget to save, otherwise you'll compile and it won't do what you think. What I could do out here now is let's just go up to the top where we create our variables, and let's make a rectangle R3. But we're not going to instantiate it at this point. We're just going to create it so it's there. Now, what I can do is say down here, actually, let's do it up here. Let's say, in order to hold on to the previous rectangle that we had with something like R1, is we could say R3 equals R1 dot copy. So what that will do is R1 will copy itself. It will make a new rectangle that is dot equals to R1 and store that in the rectangle R3. And then if down here I copy that, paste it, I could show that the third rectangle will look like R1 used to look, which is identical to how R2 already looks. So the R2 and R3 are going to print out the same values, which means they're equal, but they're not the same object. Let's save that to show the use of the copy constructor. We do have to compile both programs for sure now, although I've typically been doing that just I say for good measure, but just to make sure that any changes I've made are compiled. It compiles quickly enough that I don't mind doing extra compilations for the sake of making sure I didn't miss something. Then we run it. We see that the first two are equal because they're 1 by 1. Now we're going to change the width of the first triangle to 5. We're going to change the height of the first triangle to 7. That yields the first rectangle has a width of 5, a height of 7, an area of 35, and a perimeter of 24. And we see that the second rectangle and the third rectangle are both 1 by 1 and have a width of 1 and a height of 1 for each. And that's because we copied the first rectangle, the one displayed here, into the third rectangle before changing it, and so that we can take a look at what one used to look like. Another thing that goes with that copy is sometimes folks will create something called a copy constructor. So up here we can yet overload our constructor one more time by doing public rectangle. As I said before, all constructors will have no output type, not even void, and will be named identical to the class. This one is going to take in an existing rectangle that we're going to call R, So in the copy constructor, what we have to do is just like any other copy constructor or any other constructor, we have to set the width and we have to set the height. Now, we had a copy constructor that, created a rectangle, but it did so through a constructor and returned it. Here, we don't want to create a new rectangle inside the constructor, because how do we make ourselves that? We would only be able to do like some kind of return statement. So what we have to actually do is we have to do r dot get width to copy the width, and r dot get height to get the height. So we're literally copying each property from the passed in rectangle to ourselves. And now let's use that constructor on the other side. Up at the top where we declare all our variables, we'll make another rectangle that we call R4. And now down after we change R1, let's go ahead and say R4 equals new rectangle, and we'll copy R1. And we'll go down here, and after, let's do it after the third. We show the third one. Let's copy what we did for the first. And we'll show it for the fourth triangle. And that will show that the first and the fourth, it will visually be able to see that they're the same. We could call the equals method or the compare to method to prove that. But let's just go ahead and let's save it. Let's make sure we saved the rectangle. We did not. Save them both because we have to compile them both. And let's do the rectangle. Let's do the rectangle test. And let's run the rectangle test program. We see that the first and second start out the same. We've already copied the first one into the third one, so we're going to go ahead and change the first one to 5 by 9. And we see that the third, which copied the first beforehand, is still 1 by 1. And the fourth, which we called the copy constructor on, after we changed one, comes up as being 5 by 9. I forgot my %n, my return, my carriage return here. That's why we got the goofy looking line stuck on the end of it. It's good to see where those formatting characters really matter. So if I run it again, do the same thing, we still now it's formatted correctly. So I forgot that %n, so it stuck this. The first rectangle is larger than the second rectangle, right after the height of the fourth, or height and width of the fourth rectangle. So this really expands on this whole idea of creating objects from classes. Now we have a much more robust definition of the set of rectangles in the world. They still are defined by a height and a width. We still access that height and width through the get and set methods. These setters, getters, also called accessors and mutators, are going to be something that you just do throughout your Java programming career. But we've added to that. We've added the ability to check if two objects are equivalent. If they're not equivalent, can we find out in what way they're not equivalent? Let's be able to produce a printable string version of an object that makes sense. Let's be able to copy objects. And we still have the calculations to show other things about that object. So we really have fleshed out the full definition of this set of objects by adding in a bunch of common methods that we get really used to putting in all of our class files in most applications we create. In the next lecture, we are going to do something a little bit different. We're going to look at how we have things that are part of the class that aren't part of objects of the class. That's where that fancy static word we've been dealing with the whole time comes into play. And we'll see that in the next lecture. In the meantime, if you have any questions, please don't hesitate to reach out, and I look forward to talking to you all soon. Take care.